Hey gang, and welcome back to another worksheet solutions walkthrough for the worksheet alpha carbon synthesis practice. Okay gang, so if you're here, that means I'm assuming, at the end of looking over the alpha carbon stuff for the first time, you've been exposed to everything and now you want to put everything together and you've looked at this worksheet. Some of the syntheses maybe confused you, and that's okay. There are some big reactions, and before this, right, our main method of sticking things together was really, like a Grignard attacking a carbonyl or some type of SN2 fashion, right? The list is now growing, and that's okay, but it does, bring some more opportunity for different synthetic pathways and problems that you have to solve. But no worries, because we have our toolbox. We just need to sharpen our skills, and we're just going to go over the worksheet. The drill. We'll go over the worksheet problem by problem. What I'm going to do is I'm actually just going to throw the whole synthesis up here just to keep the video a little shorter. So we have 5 problems. Let's get to it. Okay, gang. In problem 1, right, we're easing into our first alpha carbon problem, and relationships are going to be so key, right? There's a reason why I was very annoying and talked about 1,3-hydroxycarbonyls, 1,5-dicarbonyls, and all of those relationships, or like even the 1,4 alpha beta unsaturated ketones or carbonyls. It's because they're really going to help us deconstruct more complicated synthesis problems. So if we take a look right here, ignore the middle, but this is our source of carbon over here, and we have units of 3 and units of 4, right? So before we even look at those 2 carbonyls in the product, let's see what we might need, one of each, or how to make things easy on ourselves. So over here we have 1, 2, 3, 4, 5, 6, 7. So 7 carbons total. So I think it's very easy to see that we're probably going to use one of each of these to really make our lives simple. Now, when we take a look at this, our next step, now that we've counted our carbons, is to figure out what the heck happened here. So if we take a look, hopefully you picked up on this. Okay? The fact that we can see a 1,5-dicarbonyl, I'm going to abbreviate that, screams to us that there was a Michael addition that happened here, okay? This can be your big step. So similar to kind of seeing a Grignard, like picking out an alcohol and 2 pieces being stuck together to identify a Grignard reaction as being your big connecting synthetic step. Here it's a Michael addition, okay? So now we need to kind of look at this and think to ourselves, if we take a step back, what was our enolate and what was our alpha beta unsaturated carbonyl, or enone, or whatever you want to call it. So what I hope you're seeing is 1, 2, 3, and I see, because what we should do is we should look at the alpha carbons. We know Michael additions attack from alpha carbons. So there's an alpha carbon here, and then there's an alpha carbon here. I think it's very clear to see it's that position on 2 where we have another bond, and I think you can see if we were to look at this unit right here and make a cut right here, we have a unit of 1, 2, 3 carbons, and then another unit of 1, 2, 3, 4. That makes our lives pretty simple because of the 3 and the 4 right here. So if we break that apart and then we realize that this is, where the alpha carbon that makes a bond, the 3 carbon piece should be our enolate, right? This carbon is the same one that I've dotted up here. And then we just have to realize, okay, well, if this gets attacked, that must be an alpha beta unsaturated carbonyl. 1, 2, 3, 4, double bond must be right here, because we know we need to do a 1,4 addition that's more specifically a Michael addition, okay? So now we've simplified our problem, right? So now what we can do here is just go back to we just have to work back to what we've been given. So if we look at the enolate, right, we know we create enolates via alpha deprotonation. So this is an aldehyde. We don't even have to worry about kinetic versus thermodynamic. Just throw in your favorite base. You can use LDA. You can use sodium hydroxide. You could use potassium terbutoxide, the list goes on. That will get you back to this aldehyde. And now this is really an OCHEM 1 problem, right? At least for making this piece. Step this back with PCC, we know we get aldehydes by oxidizing primary alcohols. Well, we can get a primary alcohol by doing SN2 on a primary carbon. And how do we functionalize that primary carbon? Well, we can just use the free radical chlorination, which we know will give us the majority, it will give us this versus bromination, which would give us the secondary carbon right there. Now, this piece right here, well, we can oxidize this back. If we step that back, that gives us an alcohol in this allylic position. And what you're going to see me do here I admit, I wrote this problem. Is it the best problem? Is it the most bulletproof problem? Maybe not. But remember, what I'm doing here is SN1 on this allylic carbon. And just to make sure that the double bond stays this way and we don't accidentally get resonance going and we rearrange and get the more stable double bond, I used low temperature for kinetic conditions, okay? Just a little, throw that back in there. That's why I kind of liked it, to bring that back in the mind, because we haven't talked about kinetic versus thermal control in a while. And then once you get this, right, we know we can just use NBS to brominate, right? Can't use the Br2 light and heat with the double bond, right? It'll do an addition across the double bond with the Br2. Whew, okay gang, that was problem 1. Got 4 more. Let's start 2. Okay gang, rolling on into problem 2. If we take a look up here, the first thing, ignoring the middle, we're just gonna look and see what we're given and what we have to make. So over here, we see we have a benzene ring. We see we have one over there, so I'm just gonna mentally, that check is on both sides. Then we have 1 carbon from here, and then 1, 2, 3, 4. So 5 carbons, the benzene ring, so 11 carbons total. We see we have the benzene ring over here, so that's 6, 7, 8, 9, 10, 11. Okay, so we can see we just need seemingly 1 of everything. Now, what I'm hoping you're seeing, now that we've counted our carbons, in terms of the relationship in our target molecule, is this. Okay? Remember, relationships are so important, okay? And what we see here is actually a 1,3 hydroxy carbonyl, okay? And where do we get those? How do we create that relationship? Aldol reactions, right? So knowing that this big step, which if you're wondering, do you need water here or not? Yeah, you can include it if you want to or not. But what's the big step back? It's an aldol reaction. That's how we're connecting these pieces together. Once we step that back and break it into smaller chunks, our problem gets, we have more of them, but they're much simpler and smaller and easier to work with. So what I'm hoping you're seeing is 1, 2, 3, 4, and then we have 5, and then the benzene ring. So kind of looking back and forth, I hope what you can see is we have a unit of 4 right here, we have a 1, and it's an acid chloride. So what I'm hoping you're seeing is maybe we can work with these 2 together, because I can easily stick this on our benzene ring with some EAS reaction, a Friedel-Crafts acylation, and I want a unit of 4 to work with. So what I'm thinking is 1, 2, 3, 4, I'll make my cut right here, because that also means I have this alpha carbon to attack with. Clearly that's the one that did the attacking, right? To split this aldol reaction, I will need a 1, 2, 3, 4 enolate that looks like this, and my carbonyl that I attacked looks like this, but I think you can see that that works really well in terms of taking things back to where they came from. So I think what you can see, the easiest thing is to see this benzaldehyde get created from the starting material. We're literally given this and we have benzene. So yeah, the R group here is only a hydrogen, but it works just the same as any other Friedel-Crafts acylation. So you just need AlCl3, you just need to throw in this 1 carbon acid chloride in with the benzene, you get this right there. That branch is already done. So all we need to do is actually create this enolate, which I'm hoping you're looking at and saying, that's a kinetic enolate. So if we step this back to the carbonyl that it came from, right, this 4 carbon ketone, right, we need this double bond, the lesser substituted double bond, and I did forget, probably don't need it, but good to include THF, some solvent, right? So we would need a big bulky base and low temperatures. We're thinking Chile, okay? Now, we just need to actually create this from scratch or from butane. So obviously we get ketones by oxidizing alcohols. PCC works here just as well. How do you get the secondary alcohol? The best way to do it would be SN1 on a secondary carbon with a good leaving group, and we can get that good leaving group by brominating, and we know bromine is pique, so we'll be going on that secondary carbon. Okay, gang, that was 2. Charging on into 3. Okay, gang, so in problem 3, if we take a look right here, first, obviously, let's place our carbons in terms of what we're given and what we have to make. So we have 1, 2, 3, and then we have 1, 2, 3, 4, 5, 6. So 9 total carbons. And over here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so again, luckily just 1 of everything. But this is a weird kind of target molecule. We don't see a familiar 1,5-dicarbonyl. We don't see, alpha-beta unsaturated carbonyl. We don't see a 1,3-hydroxycarbonyl. What's going on? Well, what I want to kind of highlight is we do see, I think we can see 1, 2, 3, 4, 5, 6, right? I think we can see 1, 2, 3, 4, 5, 6. I think we can place this in the target. And I think it's very easy to kind of cut that bond and see the 1, 2, 3 right here. Well, what I want you to see or think is that we have the carbonyl intact, okay? And if we look at where this new 3-carbon piece is attached, what I want you to do is 1, 2, 3, and 4, okay? It's not a Michael addition, it's just a generic 1, 4 addition, right? You can see if you start counting, it's key, this works if you only start counting from the oxygen to the 4th position, that's where this new bond was made. So we just did a 1, 4 addition with a soft nucleophile. Now, what kind of soft nucleophile? Well, we see it with some type of alkyl nucleophile, right? So obviously we can't use a Grignard. We have to use a cuprate, right? So, you know, if you don't work with cuprates in your class and you're watching this, well, this problem is designed specifically to use a cuprate. So if we take this and we step it back, we need an alpha beta unsaturated ketone here in this case, right? We need an enone. So what you would do is just imagine that there's a double bond right there. So that's what I did right here, 1, 2, 3, 4, and I have those 2 methyl groups afterwards. So, and then we have the 1, 2, 3, and you know, whether that lone pair is there or not, you don't have to show that. I'm showing it to be explicit in the solutions right here. This is our cuprate. Remember, you have twice as much of your nucleophile to the copper that you're bound to, okay? So if we go from here to here, really easily, we only have 1 step. Now, we have a good leaving group. It's on a tertiary carbon. Now remember, this is just an E2 type thing happening, but remember, we have this, you know, we can make double bonds here and here. They're the same position, or we can make one here. So we need a small base to make that SATSEF product. That's right, I'm reaching all the way back in jOeCHEM 1, but we need to do E2 with a small base, so it is, you know, it can get in here to pick off the more substituted hydrogen to thus make the more substituted double bond. The hydrogen on a more substituted carbon, I meant to say. That's why we get this. So I picked NH2 minus. This is a tertiary carbon. You could use OH minus, up to you. Now, down over here, maybe a little bit more interesting. So this is our cuprate. Now, remember, we have to make cuprates from something with a, so we know we want to have our cuprate, we want this carbon to be nucleophilic, okay? So it needs to be attached to a halogen. This being primary, you know, starting back here, I just chlorinated to get a chlorine on that primary carbon. Now here, some people like to put this little circle to be like elemental lithium. You're basically going to have a 1-to-1 ratio between this, your whatever alkyl halide you're using, and the lithium. Now comes the trickier part. You see that I've written 0.5 equivalent of copper. You need a 2 to, so this will create our alkyl lithium, okay? To create the cuprate, you need twice as much of this as you do to the copper, right? So if you know, and I just assumed we had 1 equivalent of this, which means we have 1 equivalent of this, which means we have 1 equivalent of this. So to have this be double than the copper, I just halved the copper. So that's why really, you know, 1 equivalent of this relative to 0.5 equivalents of copper is really 2, a 2-to-1 ratio. So that's why you're seeing that. Some people are big sticklers about this, which, you know, that's because it's the correct thing to do. So that's why you saw it on my solutions, okay? But that explains this whole problem. It's just a 1,4 addition with a cuprate, a soft nucleophile, to an alpha beta unsaturated carbonyl. That's problem 3, gang. 2 more, 4 and 5. Okay, gang, so in problem 4, if we take a look right here, we're obviously going to count our carbons before we do anything else, because that's how we do. So we can see 6 carbons right here, 7, 8, 9, and 10. So we have 10 total. And then over here, you can see again, 6, 7, 8, 9, 10. So it looks like we'll be using 1 of everything that we have over here. Now, if we take a look over there, we get to play our favorite game, which is what's the relationship in the target molecule. So what I hope you're seeing is this right here, right? We've attacked them, but now we're actually looking at one in our product. And remember, whether you want to call this an enone or an alpha beta unsaturated carbonyl, that's what we have as in our target molecule, which is indicative of an aldol condensation, okay? Now, you can do the condensation with, acidic conditions and an enol attacking a carbonyl, or it can be basic conditions with an enolate attacking a carbonyl with that heat involved, right? To drive off the not so great leaving group. So if we take a look right here, I think it's really easy to see, right? There's evidence of our carbonyl still left over, which is on the cyclohexane ring. The alpha carbon right here, it would make a very convenient cut to cut it right there, right? We see 6 carbons right here, and then we see 1, 2, 3, 4, which could be the 3 in this propane starting material, as well as the methane right there. So if we step that back, it's very clear that this piece has to be our, I'm going to do this in acidic conditions, our enol, right? This alpha carbon is this one right there. And of course, we need a carbonyl that gets attacked, right? So that can be this right here, 1, 2, 3, and 4. So now at this point, we have 2 much simpler problems. Let me just handle this branch first. So we make enols by acidic conditions with a carbonyl. That's just the ketone right there, right? This is our keto-enol tautomerism going on. We can get this carbonyl by oxidizing a secondary alcohol, either with PCC or the sodium dichromate and H2SO4. And then from there, SN1 with water on a secondary, alkyl bromide. And then we can make this happen with Br2, light, and heat. So now actually putting this together. So there's a little bit more work involved because we have to stick, this carbon piece, this methane onto the propane. So if we step this back, right, the way I'm going to do that is stitch them together with a Grignard reaction. So little OCHEM 1 action. So you can see right here, if I have this right here, right, we can step this back. We get this aldehyde by oxidizing a primary alcohol with PCC. And then I can split this bond, right? And we haven't done this in a while, but this is a Grignard attacking a 1-carbon carbonyl, right? There's formaldehyde, and here's our Grignard right there. We can easily get this by brominating the secondary carbon, throwing in some magnesium, THF if you're feeling it. That gets you the Grignard. And then up here, right, we just have to get this aldehyde. So again, we can use PCC. That would give us back, take us from formaldehyde to methanol. Then if we have methyl bromide, we can do SN2 with NaOH to get CH3OH. And then up here, right, we can just brominate to get a bromine on methane right there. And that rounds out 4. Gang, we have one more problem. Stick with me. Let's finish this walkthrough. Okay, gang, and our final synthesis problem, if we take a look up here, we're starting off with isopropanol and ethanol, and we are tasked with making that over there. So, before we look at all those lovely oxygens in the target molecule, let's count our carbons. So I see 2 and 3. So, we have 2 carbons, 3 carbons, so, we can use units of 2 and 3. So if we take a look over here, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 total carbons. So actually here, we're going to need to use more than 1 piece. So what might work out, and of course, taking a step back will, help us see what we actually need. But 2 of these and 1 of these would make 8. So hypothetically, I'm thinking maybe 2 of these and maybe just 1 of these. However, if we take a look at our molecule, let's see if we can find some good relationship, right? If we make a cut, we want to try to make a cut such that we'll cut a piece and have it be something that has a similar amount of, the same amount of carbons as our starting material, right? Like, we're not going to try and make a cut and have it be 4 and 4 because that doesn't line up well with anything we have, right? If we make a cut, it would be really great if it was like a piece of 2 and a piece of 6, or a piece of 3 and a piece of 5, right? That would be really good. So if we take a look over here, there's 2 things that might jump out to you, and I designed this problem for it to be like that. I think you'd see that we have the 1, 2, 3, the 1,3 hydroxycarbonyl, but we also have the 1, 2, 3, 4, and 5, the 1,5 dicarbonyl, right? The 1,5 dicarbonyl is meant to be deceptive. It's meant to throw you off because the 1,3 hydroxycarbonyl, that is evidence of an aldol reaction happening in these pieces being connected, right? The 1,5 dicarbonyl, we know that's when an enolate attacks an alpha beta unsaturated carbonyl. We don't really see evidence of that because we see this OH instead, right? If the OH was gone, it would be a Michael addition, open closed book, right? That would be it. However, we see evidence of this alpha carbon attacking this carbon right here, making a connection. And if I do make a cut here, I think you'll see that I have 1, 2, 3 carbons. Great. Even an oxygen on the middle carbon, which is very similar to what we have over here. And then a 1, 2, 3, 4, 5 piece, which could be a combination of this and this. So I think that's a very good cut to make. So if we step this back, this has to be our enolate, which is what I have right there. This carbon that I'm dotting is the carbon that's dotted over there. And then if I bring over what was the carbonyl of the attack, you'll see it's symmetrical, right? That's how I kind of wanted this problem to go. It doesn't matter which carbonyl gets attacked because they're both the same, right? So the one I asterisked right here is the one up there, okay? So I just want to like take this back to the starting material. We know how to make this enolate. We don't have to worry about thermo versus dynamic, in terms of the enolate we create because it's symmetrical. And then we just have to get the carbonyl, right? So we can just oxidize secondary alcohol to this. You can use PCC if you'd like, doesn't matter. Now, this. So if we, obviously we have to create this. This is 5 carbons long. And what I want to highlight here is that these 2 oxygens are separated by 3 spaces. So if I were to step this back with PCC, I think what you're going to see is one of these 2 could have been an alcohol beforehand, right? The reason being is if we step this back with some type of oxidation, right? This was always a carbonyl, but this might have been and was an alcohol, the result of, yes, another aldol reaction, okay? So that's how we stitched these 2 pieces together. We had a first aldol reaction, which then fed into we oxidized, which fed into a larger aldol reaction. So if we take a look right here, if we were to chop this in half right here, this could be our alpha carbon that did the attacking. This was the carbon that got attacked in the carbonyl. That's this carbonyl right here. If I were to step this back, it's a 2 carbon piece. And then we had, yet again, this same enolate, which I already created up here, so I can just repurpose it. I don't have to show how I made it again. And then to get this, just some PCC to bring it on home. Whew, gang, thank you for rocking with me through this synthetic journey. If you were looking for some questions or how I approached the problems, I hope you found them here. If you're watching this video, that means you have financially supported jOeCHEM when you didn't have to at all. So I just wanted to say, first of all, thank you for using the website. I hope, more importantly, you're getting out of it what you planned to or wanted to, and I hope you are understanding carbon more as a result. But thank you for, financially supporting the website. You don't have to watch, nor do you have to give me a single cent. So I really, 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 really appreciate that. I'm so happy you're using jOeCHEM now. I hope you're using it to the end of your organic career. But no matter what, I hope to see you all in the next video.